What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. I got a rock. 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 I got a rock. I got a rock. I got a rock. Rock.
What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. A rock. I got a rock. I got a rock. Got a rock.
What did you What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock. Got a rock. 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 I got a rock. I got a rock. 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 I got a rock. Got a rock.
All right, so today we're going to start on the next module, which is going to be actually pretty short. Probably won't be able to get through it the entire thing today because it builds on stuff that you've already seen before. File input output. Remember that we are on Piazza and we are on YouTube, so if you have any questions, please go ahead and post there. Otherwise, a file basically is everybody understands what a file is. A file is usually is a unit of stored memory, usually on disk, but it doesn't have to be on disk. Of course, when you open up a file, right, it doesn't just exist on disk, it exists in memory as well, right? But not only are files like, opening up a Word file is a file, a text file is a file, your source files are files, right? Files are also directories, at least in the Unix world. It's just a way of keeping track of files and keeping track of files in a hierarchy, a file hierarchy, subfolders, subdirectories, under subdirectories, etc. But also, programs are files, right? Programs that you actually run, right? First of all, it's stored in machine code on a disk, and then when you actually start running a program, that program gets loaded up into memory. That program is a file that exists in memory. You also have buffers. Right? Buffers are files that you can write to and then read from. You have file input, and then you have file output that you can read from. One of them that you've already been using is the standard input. When you sit there and you mash the keyboard, you type A, B, C, D, right? That input gets put into a buffer, and only when you call, say, scanf or some other method that actually reads from that buffer does it start pulling data out of that buffer. You also have what are called sockets, right? Sockets are files. When one computer talks to another computer, they do so over a network. The way that they do that is by opening up a socket, and the socket is a file. So one computer will write to that file, to that socket, and then the other computer on the other end will read from that socket. So everything that you do with networking can be seen as file input and output. The standard input is a file because you can sit there and mash the keyboard like a buffer, and you can read from that file. The standard output is a file. You can print to the standard output, and that gets put into a buffer, and then eventually gets flushed and printed out to the screen. Right? So a lot of files that you've already been dealing with. Files may be read, that is file input, or written to, that's output. Right? That's simply what we mean by file input and output. We're going to keep it simple. There are situations in which you can read and write the file at the same time. You can append to the file. You can go through and seek and rewind throughout the file. We're not going to get into that. We're going to keep it very, very simple. Right? Not only that, but you have different types of files. You can have binary files or plain text files. Files may be binary. Right? This is binary, excuse me. This is pure data. Right? For example, a GIF file or an image file, an audio file or a video file. We're not going to be dealing with that directly. If you want to write a program to process audio, or you want to write a program to process an image like you've already done, all right, in your previous hacks, then you're bringing in a library to do it. In fact, if you look back at those hacks when you were doing image manipulation, we brought in a library. We didn't write most of that code. We wrote the glue code that connected to that library and used the library to load up a JPEG file and save a JPEG file. Right? If you want to look at the details of how that binary data goes back and forth, you can look at how that library is implemented. Otherwise, 99% of the time, if you're going to be dealing with binary files, you bring in a library to do it for you. Right? We're going to be dealing with plain text files. Plain text files. That is just ASCII text, right? Where you are writing text to the file or reading text from the file. It could be numerical data, but you'll, just like numerical data can be entered from the command line, you'll end up having to convert that numerical data using A to I or A to F or whatever, right? Files, even plain text files, may be structured and not intended for human consumption. So what I mean by that, let's go ahead and take a look at an example here. We just got done with string processing. What kind of data is this? What kind of formatted data is this? It's tokenized, and what's the token in this case? It's a comma, right? This is CSV. This is a CSV file. Now this is not necessarily intended for human consumption, because it is very difficult to read, right? You would have to you'd have to look at this and tokenize it. Well, who's the author of this book? Well, okay, I have to go over here. Oh, it's Paul Hudson, right? And it's within quotes here because we're going to have a comma within that, right? Paul Hudson. That's not a delimiter there, right? You'd get confused. You'd confuse yourself and very, very easily. This is intended for human consumption. This is just a table. I took the same data, threw it up here, and asked it to convert it into an HTML table for me. Right? Now, this is how humans generally consume this kind of data. This is not intended for human consumption. But also, it's not that great of a data format. There are some alternatives. Here's the same data, but in JSON format. JSON stands for JavaScript Object Notation, and it is the de facto standard for web stuff, basically, for representing data for JavaScript and web development and stuff like that. But it's also used outside of web development because it is a good way to represent data. You'll see here that it's a list, and so we're using the square brackets just like C does. for indices, that is. And then I've got an opening curly bracket, a closing curly bracket, commas. And then within that record, I've got a key value pair. What is the course associated with this book? String, colon, and then the value, comma. And then on the next line, title, right? Each one of these is a key value pair. There's also XML, right, which you'll be working with in your lab this week. Not as input, because even if you were doing XML input or JSON input, I'd say bring in a library to do it. You'll just be doing simple output, formatting an XML file. And this is structured hierarchically. I've got these what are called tags. This root tag is books. So everything within this tag and the closing tag way down at the bottom, right, is a record in this node, basically, is what they're called. Each book is represented by its own tag. Here's a book. Here's the end of that book. Here's the beginning of that book's data. Here's the end of that book's data. And so each one of these is a opening tag and a closing tag. Within that, you've got the actual marked up data. This gives the data semantic meaning. Instead of just a CSV file over here, with everything is implicit by the header and the order, that the first one is obviously the course, the second one is obviously the title, but that's only because it's up here. Each one of these elements is actually semantically marked up. This is the course. Everything between the opening tag and the closing tag denotes that piece of data. Right? And then you can set this all up as a hierarchical data where you've got data, subdata, 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 as much as you want. Right? You can get quite complicated, which is why you would bring in a library to do most of this stuff. But the takeaway here is that a lot of it is not intended for human consumption. Again, for JSON or even CSV is not really intended for human consumption. XML, JSON, etc., or even base 64 encoding. Ever wonder how an image makes it through your email when somebody emails you as an attachment? Well, email is not. Email is based on SMTP, Simple Mail Transfer Protocol. It is not intended for binary data. So what you have to do is you have to take that binary data, translate it into textual data, and then send the text over the email. And if you ever get an email, you can look at with an image attachment, you can look at the raw email, and you can actually see the base 64 encoding. Base 64 is going to be A through Z, uppercase, lowercase, that gives you 52 characters. 0 through 9 gives you 10 more, so you're up to 62. And you just need 2 more, and I forget what they are, like underscore or something like that. And maybe not ampersand, but something else, to give you 64 text characters that can represent this image data. Right? And that's how it actually works. But definitely it's not intended for human consumption. When it gets to the other end, it's decoded, and then the raw image is displayed to you. Right? That's all transparent if you're using an email client of some sort. But in any case, you would bring in a library to do all this. All this is part of something called EDI. EDI is Electronic Data Interchange. Not everything is going to be written in C. Not everything is going to be written in Python or Java or whatever. There are dozens and dozens of languages out there, and each one of those languages needs to speak to each other in some sort of universal data format. If you want your C program to send data over to a Java program on a different computer, you need a way of talking back and forth. At least the data part, right? If you want to send data from one end to the other, you need a way to exchange that data, interchange that data in an electronic format. And to do that, you would choose one of those serialization formats, okay? But again, what we're going to focus on is plain old text files. There are 3 basic steps to working with files in C. 1, open the file. 2, process the file. Now this could be for reading or it could be for writing. Again, it could be for both, but we're not going to go that far, right? You could jump ahead, read, and then start overwriting. We're not going to do that though. We're either going to read or we're going to write. And then finally, 3, you need to clean up after yourself, so you close the file, right? We're going to look at each one of these steps in turn. We're going to look at the easiest one, 2 first, opening a file. Right? So a file in C is represented by a pointer, a built-in, not a built-in pointer type, but it's in the standard input-output library called file star. You know that it is a pointer. How? Because of the star, right? And you know that it's a file. How? Because of the name. Right? I think that it might be a macro. I'm not sure. You'd have to look at the implementation. But it is FILE, all uppercase. Why is it a pointer? Let me come over here to this file. Initially, when you open up a file, there is a pointer pointing to that file somewhere in memory. At the beginning, it points to before the first character. As you start reading character by character by character from this file, the pointer advances in the memory. If you read one character, then it'll advance to the next character. If you read another character, it'll advance to the next character. If you read an entire line, it'll go to the next line, at the beginning of the next line. Right? So that's why it's a pointer. A file is stored somewhere in memory. When you load it up into memory, you've got a pointer pointing to the beginning, and as you read the file, you move through that file. Okay? As you write to the file, the pointer also advances automatically for you. You don't have to worry about that. It's built into the standard input-output library. To open a file, you use fopen. There's a function called fopen. What do you think it stands for? File open, right? The fopen function takes two arguments. A string representing the path or file name of the file you want to open. Right? And the second one is a string representing the mode, right? So a mode, we'll deal with the easy one first here. A mode can, for our purposes, we're going to stick to two modes. A mode can either be R. What do you think that's for? Reading, right? And reading is input. Or it could be, I will go into code mode here. W, the other R, right? Reading, writing, arithmetic. So the other R here is W, and that is for, what do you think? Writing, right? That is file output, okay? What about that file name, right? Or upon success, I should say, it returns a file pointer to the file, right? Sometimes this is referred to as a handle. So in some examples, especially in some tutorials, they'll use an H to indicate that it is a file handle as a variable name, right? And H is just short for handle, okay? So let's go ahead and close all these data files now that we're done with them. And let's go ahead and start with an example here. I need a file to work with here. So let's just go ahead and open up that CSV file, right? Because we know the contents and we can verify that we're actually reading it correctly if we end up reading it. So let's go ahead and open that up. I'll go ahead and just use the F here. I could call it my file, or I could call it the input file or something like that. I'll just keep it simple here, F. And I'm going to call fopen. Again, I'm going to provide it two arguments. Both of them are strings. If I'm doing this for reading, obviously since the file already exists, then my mode is going to be R. Now, what about the file name? I am in the current working directory here. Where am I? I'm in main, right? And there's my file right there, books.csv. And so I would simply just open up books.csv. Right? This line of code opens the books.csv file, assumed to be in the current working directory. CWD. CWD. Right? If it's not in the current working directory, I wonder what happens. Right? What happens when it's elsewhere? So I'm going to go ahead and write a check for this. Ooh, oh no. I didn't do anything to it, so I don't know. So if F is null, then it failed. Right? Again, remember, upon success, it returns a valid pointer. Upon failure, what is the only invalid pointer that it could possibly return, just like malloc or your functions that you've been designing? Null. So I'll go ahead and print an error message here. unable to open file for some reason. Right? Let's think about that while I write the other part here. Why wouldn't you be able to open a file? What do you mean by corruption? That you have to pay the bribe to get it to get him to open it? You have to pay a toll and bytes. Should I be able to read any file I want? There are sensitive files on the system. One of those sensitive files is the Etsy password file. Right? Now, this is not all that sensitive. What I'm going to do is I'm going to start listing the passwords of everybody on this system. Right? Don't worry about it. That's where they used to be stored. They've been redacted for a very long time now, and passwords are no longer stored in the Etsy password file, but metadata about each user is. If I went onto the CSE server, I could find not that much personal information. I could find your first name, your last name, and then your phone number, your address would actually be the department's phone number and department's address. They don't put your personal stuff in there. But I could find out, what your shell is. For example, root here, their shell is bash. Right? You can change your shell if you want to. I'm Ubuntu here, so grep Ubuntu. Everybody is Ubuntu on their CS50 IDE. And you see here what information you can find out. There's the username. There's the redacted password. There's the user number and the group number. There's their home directory. And there is their default shell when they log into the system. Right? Not that much information, but there's enough there that you maybe you're interested in it. Now, that's not sensitive. I was able to read that and look at all that stuff. What's really sensitive is where the passwords are now stored in the Etsy shadow file. It's a shadow of this file that you're not allowed to see because, just like a shadow, it's just a lack of light. Right? It's a blank thing that you can't look at. And clearly, permission denied. Thankfully, I'm not able to look at even if I were able to look at the passwords, they would all be encrypted. So there's at least one level of security there. This means I can't even look at that file. If I attempted to open up that file, what do you think would happen? It would end up returning no, and you would not be able to open up that file. So let's go ahead and compile to see that I can successfully open up my own books file. Demo. I'll run this and success. Right? I was able to open up that file. I'll go ahead and leave this in for the notes. But otherwise, let's go ahead and try opening up another file. Let's try opening up that sensitive file, that Etsy shadow file. Right? Compile again, and let's see if this works. Unable to open the file for some reason. I don't have permission to. Right? What's another possible scenario? Before I ask that, actually, note how I gave the file name here. I started at the root, and then I went under the Etsy directory, and then I went to that particular file. So you can also use what are called absolute paths. Right? You can look at any file in the system and open it up there. Not the current working directory, not in this main directory that I'm working in, but in that directory over there. You can also open up files in a relative path. So let's do that one. You can use relative directories. Right? So what I'm going to do is I'm going to open up a file one level up. Right? So the current working directory, then one level up, and then I'll go into another, honors, and then slash or foo.txt. All right? So let me go ahead and expand this out. Do you see a foo.txt file if you really squint since it's really small? I can assure you that there is none. Is this going to work or not? Am I going to be able to open up a file for reading that doesn't exist? Unable to open up the file for some reason. What's that reason? It doesn't exist. So if you don't have permission, the file doesn't exist. whatever other reason there might be, corruption, whatever that means, right? Then it could fail. And the only way that you'll know if it fails is by checking to see if it was null or not, okay? So you can open things up in the current working directory. You can open things up using an absolute path. You can open up things using a relative path. Go up one level and then go over to that other directory called honors, and then within that directory, open up the foo.txt file, okay? I'll bring this over here into the notes. There we go. All right. So some observations here. Opening a file for reading may fail, right? It may not exist. You may not have permissions, etc. Right? Opening a file that doesn't exist for writing, however, is a different story. We'll actually end up creating that file for you. So let's go ahead and see that in action over here. So I'm going to go ahead and get rid of this. In the current working directory, there is no foo.txt file. So if I were to open it up for reading, of course this would fail. But if I open it up for writing, okay, fine. What are you going to write to it? Go ahead and start writing. Do whatever you want to do to it. When I run this, you'll see over here that a brand new file will magically appear. Foo.txt. Now what's in that file? Did I write anything to it? No. But the file was created. Okay? So if the file already exists, by the way, here's another gotcha. Hello, how are you? Today is Monday. Right. There's some contents in that file. Let me go ahead and run this program again, but before I do, let's guess to see what's going to happen to that file. Open it up for writing. You don't write anything, and then your program is done. Bye-bye file. Right? Yeah. What did I do? I opened it up for writing, didn't write anything. It ended up closing it for me. Right? 99 times out of 100, it'll do that for you, but it's best practice that you do it yourself. We'll talk about that in a second. But it got overwritten. So if it opens up a file for writing that already exists, whatever is there will be overwritten. There is no undo, there is no backup, there is no recycle bin or anything like that. Be careful, right? Opening a file for writing that already exists will overwrite or clobber the contents of that file. So this is a term of art used in the Unix world a lot, clobbering files. You've got to be careful. You're clobbering, you clobber something, you hit it, you destroy it, you ruin it, right? That's what clobbering a file is. You are getting rid of the contents of that original file. So be careful. You are overwriting that file and there is no undo. And guess what? Let me go ahead and cut and paste this so that I have it. What if I open, I don't know how to do file IO. Is it demo.cse or demo.c, right, for writing? What am I about to do? I just deleted all my work, right? Be careful, don't do that, right? Make backups. Make sure that you are not opening up any of your source files for reading or writing. Foo.txt, there we go, okay? So, once you're done, now we'll skip step 2 because it's magic for now. But step 3, immediately jumping to step 3, is going to be closing a file. Once you are done with processing a file, be sure to close it. Right? Failure to do so, it could result in file corruption. Right? So files can be corrupted. It could be that you've got stuff written to a buffer, and then the file gets then the program ends before that buffer gets written to the flushed to the actual file, and now your file doesn't have all the data that you actually wrote to it. 99 times out of 100, again, the system, the operating system will save you from yourself. It's that one time that's important, what is it? Somebody's law. Murphy's Law, is it? The one time that you need it to actually work, it fails, right? Anything that can go wrong will go wrong, but only at the time that it's the worst possible impact, right? So how do you close a file? If you open it with fopen, how do you think you close it? Close, right? Use close to close a file, right? Pass it the file handle / pointer. Right? So let me come back over here to our example. And once I have done, I'll to do process the file, and then 3, close the file, right? And how do I do that? For close, and I will pass in F, the file that I want to close, right? Another reason that you might not be able to open a file is because it has a file lock on it. So so think about opening up a Word file, right? And you're sitting there typing your essay or whatever, and you hit save. I don't want to do this assignment anymore. You go onto the desktop, you leave it open in Word, you go to the desktop and you try to delete that Word file. Now, have you ever experienced that? What's going to happen? Are you going to be able to delete it? No, because a current program has it open. It has a lock on that file, and you're not able to do whatever you want to do with it because until that lock is released. That's another situation in which you might not even be able to open up the file, or it might even actually block your program until that file becomes available. Right? So make sure that you're opening and closing files properly. Sometimes failure to close a file could actually leave the lock on it. I've experienced this mostly with Windows, actually, where Word crashes, but it crashes in an indeterminate state. And so this is old school Windows, maybe not anymore. And I'm never able to delete this dang file that I want to delete because the file lock is on there. The program that could release that lock is no longer in existence, and so I'm stuck. Right? And then generally you have to restart, and then all the file locks get cleaned up or something like that. And it can be quite frustrating. Make sure that you are closing all of your files. Right? All right. So again, close the file. You just use the following. I'll make sure, it's pretty simple, but I'll make sure that it's in the notes here. All right. So how do you actually process a file? Let's go ahead and go with file output because it's really, really, really simple. Then we'll save the harder one, file input, here for the sequel. Right? To keep it simple, again, there are dozens of ways that you can do this. I'm going to show you the easiest and most straightforward way. To keep it simple, use printf. Looks familiar, right? Printf. But there's an F in front of it. What do you think that F stands for? File. So instead of printing to the standard output, you print to a file. Right? Everything you know and love about printf can be used with fprintf. All of the placeholders, all of the modifiers, printing pi out to only 2 decimal places, printing something with extra space, printing a tab, printing an endline character. Whatever you want to do with printf, you can now do with fprintf. You just have to be careful because it takes another parameter to the function. So to do that, let's go ahead and go back to our IDE over here, and let's get some data that we can actually process. Right? So I'm opening this up for writing. Again, it's file output. I've got an integer, I've got a double, and I've got my name there. Right? Let's print all those things out to one line. Normally, if I use printf, I can format x using %d, or x is equal to %d. Pi to, 3 decimals is %.3f, right? And then hello %s for my name there. And then I would provide x, pi, and name. Right? Making sure to close the file, but I already have that code there. Now, what's in this? I'm opening up foo, right? Yep, I'm opening up foo here. What's its contents? Nothing. So let's go ahead and compile this and see this in action. Right? Of course, the file is unchanged, but you can see what I did here. Right? That's because I used printf. Now, take that knowledge, copy paste that knowledge to use fprintf. The only difference is that you add the file that you want to print to first. Once you do that, it's not going to print to the standard output anymore because I'm not using printf anymore. I'm printing to the file instead. Success is still being printed up here, but now the file, the contents of that file is exactly what I output to the standard output instead. And instead of the standard output, it is now in that file. You can go into a loop. You can print as many lines as you want. Don't get caught in an infinite loop, because if you get caught in an infinite loop or a very, very long loop and you are printing stuff to a file, the file gets bigger, 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 bigger. There are limits to how big a file can be, especially on CSE where you're throttled to, I think, 4 gigabytes. Once that happens, any attempts to exceed that size, hopefully it'll kill the program. I mean, a lot of you have seen that with respect to the Apache web server, that message that you've exceeded 137 megabytes of output, right? You are overflowing a buffer at that point, but a buffer is a file, right? Okay, so there's that example. I'll go ahead and put that in the notes as well. Make sure that you are closing it after you are done. Don't close it until you are done. If you close a file and then you still need to write things to it, well, then you need to reopen it, and guess what happens when you reopen it? You're all the way back at the beginning. So don't close it prematurely. There are some other functions that we're not going to cover that you can go ahead and go down the rabbit hole and find out all about them if you want to. They're called man fseek. Seek, there we go. So get position, fseek, rewind, right? Seek and rewind, you can go back and forth in a file as it's open if you really want to. You can jump all the way to the end if you really want to, and then start appending. I'm not going to get into this because I want to keep it simple, but I do want to make you aware that these are available and you can read all about them if you want to, and you can use them if you want to. I will draw your attention to one thing though. Seek and rewind, where are those terms from? All right, so maybe, has anybody in this room ever owned a cassette tape at all in their entire lives? Okay, one, 2, 3, 4. All right. So think back 30, 40, 50 years, and how was stuff actually stored? These big, giant tape decks, right? And they were all magnetic tape. To this day, by the way, magnetic tape is still the cheapest form of long-term storage for data. It is not solid state drives. It is not CDs. Per byte or per kilobyte or whatever your measure, those are still going to be the most cost-effective thing that you have. Even as of, I think, 5 or 6 years ago, our sysadmins kept tape backups of all the CSE archives. I don't know if they do that anymore, or if they've but Charles Daniel used to keep all the tape decks at his home, right? These big giant reels of tape. And that's why it's rewind, because you're rewinding the tape, or you're seeking, you're fast forwarding the tape, right? So that's where those terms come from, right? You still have those terms when you've got your digital version of it. You can fast forward and you can still rewind, and you still use those terms because it's from tapes. It's just that it's not actually physically rewinding and fast forwarding anymore. Okay? All right, so that's file I/O, or file output, excuse me. File input, the other one. Again, there are many ways to do file input. Most of them are extremely dangerous. So I'm going to limit it to 2 methods that are safe, right? 2 simple, safe methods are to use either fgetC or fgetS, or forgets. FgetC forgets, it doesn't roll off the tongue there, but fgetS Forgets, right? That's a nice way of reading it. So what do you think that these stand for? Well, obviously the F's in front of them stand for file. Get, you're doing file input, you're getting the contents of the file. But what do you think that the difference between C and S is? You're getting one character in the first one. S is you're getting an entire string. And in that particular case, you're getting an entire line of a file. Right? Now, in detail, we'll look at each one of these methods in detail. So fgetC, as you guessed, gets a single character from the file and advances the file pointer to the next character. Remember, this is why files are file star. It starts at the beginning, you read a character, it moves over to the next character. You read the next character, it moves over to the next character until it reaches the end of the file. At which point, there's nothing else to read, right? It reads one character or byte at a time. Right? It returns the character that it read. Right? So you do have to capture the output value. And finally, when it reaches the end of a file, it returns a special character. This character cannot be found in the ASCII text table because any character in the ASCII text table could be in a file. So we need a different special type of character that's not really a character to tell you that you're at the end of a file. Right? So, end of file. How do you think we should represent that? No, this is not a pointer. It's going to actually it returns a character it read. That is going to be a char. Right? That is definitely a character, not a char star. fgetS, that returns a string, and that will be a pointer. But this cannot be a pointer. So it returns this very special character called EOF. And that sets you up to actually design a loop that you can read character by character by character and do whatever you want with those characters. And then until you reach the end of the file, EOF. Once it reads EOF, you're done. You're at the end of the file. There's no more reading to be done. You could rewind, I suppose, but you already read it. You're done. Right. So let's go ahead and demonstrate that. Questions so far? No? All right, remember that the foo contents are over here. So let's go ahead and, now I won't overwrite it anymore. Let's go ahead and process the file by reading it in. So read it in character by character. So to do that, let's go ahead and read the first character. I need, of course, a character to store it. And I'll start out with one call to fgetC. And it only takes one argument, the file that you're reading from. Not the file name. You already gave that to Fopen. Fopen gave you a file handle to read from. So we're going to start reading from that file pointer. And then process it. Do whatever you're going to do with it. I'm just going to print it out. %C and the line. And print C. Let's go ahead and do that a couple more times. Right? Each time I do that, I'm not going to declare C. In fact, I'll do it 1, 2, 3, 4, 5 times. Right? And let's run it. So what are the first 5 characters of foo? X, space, the equal sign, 4, and 2. So that's what I'm expecting it to output here. X, space, the equal sign, sorry, I missed that space, and then 4. Right? There was a space there, right? Yep. Sometimes you overlook the spaces because they don't, you take them for granted. Right? All right, well, that's 5, so all I need to do is cut and paste this a couple dozen more times, right? Should I be doing it like this? No. How should I be doing this? With a loop, right? What kind of a loop do you want? A for loop or a while loop? While, okay, you immediately jump to while. Why does that seem more natural? You don't know up front how many iterations you're going to be doing. While you're still reading something, while you're not at the end of the file yet, read the next one, read the next one, read the next one. Right? Once you get to the end of the file, that's when you stop. So while C is not equal to that end of file character, print out whatever you have so far, and then get the next one. And I could even keep a counter if you wanted to. Let's go ahead and do that, actually. Int count, or number of characters, number of bytes, whatever you want. I'll initialize it to 0, let's say. And then I will increase the count each time I read a character. And then let's go ahead and print that out at the end. Printf read %d characters count. There we go. All right. Now this one should go all the way to the end of the file. And it does. It looks like B-O-U-R-K-E. That was my last name. And then what's at the very end of the file here? No, null terminator. You can put null terminators into a file, but you shouldn't because they're not printable. That is only in C that you need to do that with a character array, with a string. Right? So I'm going to the next line, right? So there's a next line character. Right? And where is that being printed here? Well, right here. It's going to the next line. That's why it's a blank line. Right? And it read 54 characters. Are there 54 characters in here? If you look really small, this is the 54th column. So there are 54 characters in there. Another way that you could do this was by typing lsla foo.txt tells me that it is 54 bytes. Right? I could do a word count on foo.txt. It'll tell me that there is one line with 12 words and 54 characters total. So I'm convinced my program works. Right? Excellent. This is how you can go all the way to the end of the file, reading character by character. Now that's not always what you want to do. Sometimes that's perfectly fine. But sometimes you don't care about character by character by character. I want to read in an entire line, say, of a CSV file so that I can process that and tokenize it and get each one of those tokens. Right? And if you want to read an entire line, then you need another tool. That other tool was fgets or fgets. Right? So let me go ahead and start a sub heading here, fgets. There we go. So fgets works differently. Fgets gets up to an entire line of the file at once, but limits itself to a certain size. Right? Let's just go ahead and go. I'm just going to go ahead and give you the signature of this function. Right? So it returns a char star. What is a char star? It's a character pointer. We call those things strings. It returns a string. It returns the entire line. Right? But how does it do it? The first input, the first parameter, I should say, parameter, is the buffer or string where the result will be stored. Right? Forgets the, actually, let's go ahead and go with the second character. The second is the limiting size. Right? Generally, the size of the buffer. If your buffer is big enough to hold 1,000 characters, then you'd better not read more than 1,000 characters. Because if you do, what happens when you've got a string of length 100 and you try to copy a string of length 200 into it? Is it going to fit? No. So this is why this version of this is safe. The behavior is as follows. It will read at most size -1 characters from the file and place the results into S. Right? If it encounters the end line character first, then it stops. Right? So if you get to the end of the line, if your buffer is 1,000, but there's only 100 characters in the line, it'll stop. Right? You told me to read up to 1,000 characters, but I also reached the end of the line. That's it. Right? Then if you want the next line, you're going to have to call forgets again and again. Right? Why size -1? What do you think? the null terminating character. Forgets will insert the null terminator for you. The null terminator for you. That's why it's -1. So if you say you have a buffer of size 1000, really you can only handle lines of up to 999 characters because you need to accommodate that null terminating character at the end. Okay? Let's go ahead and see it in action here. So I'll need first of all, I'll need a buffer, char, and I'll just call it buffer. And I'll just make it big enough to hold any reasonably sized line. If you've got files with really, really long lines, 1,000 or more characters, then you'll have to accommodate for that somehow. You'll have to do something more sophisticated, but at least for our exercises, we're not going to throw that at you. All right? That's why, in fact, a lot of editors will say that this is a file with really long lines. Beware. You could have 1 million characters and they're all in one line. Don't do that. Right? That's a badly formatted file. Right? But I'll create this buffer that's big enough to hold it. Why do I create it statically here? Do I worry about cleaning it up? No, I'm in my main. When this program ends, this memory will be cleaned up for me. An alternative would have been to create a dynamic buffer, right? And call malloc ... I don't need that for this demonstration. Okay? All right, so I need to call forgets, and I need to capture the return value there. I'll just call it S. Or actually, I'll call it line, because that's what it is. And I'm going to call forgets. Remember that the first one that it takes is the buffer that you're going to be reading into. So, buffer. The second one is the size, and in this case, that size is 1,000. Right? You can put that into a variable if you want. And then finally, the third one that I didn't mention is, because it's pretty straightforward, that's the file that you're reading from. So in this case, it's going to be F. And we'll print it out. Printf line is equal to %s and the line. Okay? Let's go ahead and see if this works. There, it worked. But that's only because there was one line in this file. Let's go ahead and change it so that we're reading from this books file instead. Books.csv. And run it again. And there's the first line. Now let's get the second line. Cut, paste. There we go. Line or buffer. Let me go ahead and change it to buffer. There we go. Let's get the third line, the fourth line, and see what how this works. And then we'll fix this. There we go. So, thinking in Java, introduction to programming using Java, Java programming. Those indeed are the first 3 lines here if you take a close look. Why is it printing it like this though with those extra end lines, those extra blank lines? There's an endline character right here, right? In the file. And then I also print an endline character when I print it out. That's why I'm getting 2 endline characters. What does that tell you about forgets? What does it do to that endline character when it gets to it? It keeps it. Right? So if you don't want it, then you need to do what's called chomping it out. Right? But let's make a note of that. Forgets will retain the endline character in the result. Right? If you don't want it, chomp it out. Chomp it out. So this is another term of art. I think it's from Perl, because the Perl has this function called chomp that you can remove white space, trailing white space and leading white space and something like that. But how could we chomp this out? So I'll get it, and before I print it, I should go ahead and chomp it. How do I do that? I want the last character to be equal to the null terminating character. How do I get the last character? So HELLO, end-line character. How do I get that end-line character? I need to know how long the string is. I need to know the length of the string. And so it would be strlen of buffer. Right? Now, HELLO, and then the end-line character. One is 1, 2, 3, 4, 5, 6. But it's indexed 0, 1, 2, 3, 4, 5. So what should I do to it? Minus 1. And in fact, I'm only going to do that if it's the actual end-line character. If this character is equal to the end-line character, only then will I chomp it out. You can set yourself up with a loop that if there are 50 spaces and 50 tabs and then the end-line character, you can chomp all of those out, but of course you would need some sort of a loop to do that. Right? And I'll leave that as an exercise for you. But I don't want to do this over and over and over and over again. Let's limit it down to just one chunk of code, another while loop here. Right? But it's a little bit different condition now. Right? We're not returning a single character that we can compare to EOF. Instead, what is its return type? Char star. So when it gets to, what's the only thing it can do is say that this is not a valid string? No. No, not the null terminating character, because that would be a char. This is a char star. The only thing that is invalid with stars, with pointers, is null. While the line is not null, then read the next line, well, chomp it, print the next line, and then of course set yourself up for the next call. Line is equal to the exact same call as up here. Okay. Now we should see the exact file contents all the way down to the end. And we do, but of course because I've got a small window here, it's not going to be well formatted. But you can see that the last line there, 477, matches the last line over here. So if you needed to process this CSV file, how would you go about doing it now? After or instead of chomping it out, you would call, what was that function again that allows you to process CSV? str tokenize, right? And so you could use something like that to actually process each one of these pieces of data, get the first one, get the second one, get the third one, etc. Of course, you would have to do that inside this while loop. All right? So here is an example of using forgets. And don't forget it. Haha. All right? So again, when forgets reaches the end of a file, it returns null. And you can use that in your while loop to determine how many lines there were. I didn't keep a counter for this one, but you can, do the same trick as before and verify that it's actually doing what you want to do with word count here. There should be 12 lines. You can count all the number of lines if you want, and then output that and make sure that you're reading the file correctly. Okay? All right, well, we have enough time here that I'll quickly mention it, because you will be playing around with it in your lab tomorrow. But again, binary data in C. Binary data should be handled by libraries. Right? If you are actually going to do anything practical, bring in a library to do it. Right? But if you do need to handle raw data, the way that you do it is through for read and for write. Both of them have the exact same signature. For read, there we go. Yeah, here's write, right? So now I have to remind myself. Here is the data, the raw data that you want to write. Here is the number of bytes that you actually want to write. Here are the number of bytes each item takes, I should say. Here are the number of items that you want to write. And here is the file output stream that you actually want to write to. All right? So let me just show this to you as an example. All right? We'll open this up. We'll open up books or numbers. dot bin. Right? Dot bin just for binary. Right? Forget about this. Here. All right. I'll have int x is equal to 2.147 billion. 1, 2, 3, 1, 2, 3, and 1. There we go. So one of the larger numbers that you can express with an integer. What I'm going to do is I'm going to write to this. The return type tells you how many bytes that I actually wrote upon success. The first one is going to be a pointer to the thing that you want to write. I want to write x, that one number, to the file. Is that going to be right? Here, let me back up. Is x a pointer? Don't worry about restrict. Pointer. Is x a pointer? Nope. How do I take a regular old variable and make it into a pointer? Ampersand. Now, how many bytes does an integer take? Size of int. Good. Not 4. Right? That's not interoperable. That's not best practice. How many of them do I want to write? There's just one. Right? And the file that you want to write it to is f above. And I'll take all this out because that was plain text output. Let's go ahead and try this now. Oops, segmentation fault. Why? Oh, unable to open the file for some reason. Why? Why can't you open up numbers.bin? Touch numbers.bin. Okay, we'll try it one more time. I can create that file. Why can't you? That's probably the CS50 IDE restricting file extensions of some sort. Once it's there, though, I was able to open it up successfully and actually write to it. I'm sure that it won't let me open it up in the IDE because it's just going to be a pure binary file. Oh, it did. Okay, I take that back. But there was nothing in it, apparently. ls la numbers.bin. It did not successfully write to it either. Fine. Why? B is not necessary. Well, maybe it's necessary under Ubuntu, but not. Oh, duh. Thank you. You said RB, RB or WB. Yeah, if I'm going to do output, I should be doing W, of course, right? Sometimes you do, and it might be that Zybooks told you to do that as well. That's only necessary on some very niche systems, as far as I know. But in any case, let's just go. Let's try it with Ubuntu here as it is. Run it. There, success. And no, not numbers.bin anymore, but numbers. And oh yeah, it allows me to even open it up, but it's a bunch of question marks. Why? Because it's just pure binary data. Now, if I were to ask, what kind of file is that? No line terminate international EDCIDI blah 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 text, right? So it thinks it's confused because it doesn't know what it is. If I were to actually list out the contents of that file on the command line, numbers, okay, it's not going to print it because it's not going to print that 2.147 billion number because that was ASCII text. If I asked how big that file was, predict, how many bytes is that going to be? So I wrote one integer, right? And 32 bits. And so how many bytes? 4. And there it is. 4 right there. What if I wrote that over and over and over again? There would be 4 bytes per file. Now, what if I did that as text instead? What if this were represented as ASCII? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters. How many bytes does it take to represent 10 characters? 10, right? One per character. So which one is more efficient as far as storage goes? Binary, and that's why we use binary, right? But also because binary data actually represents non-textual stuff like images, audio, video, etc. Right? But even if you've got data like this, maybe storing it as binary is going to be more efficient. It's going to be more efficient on space, And consequently, writing and reading is going to be a hell of a lot more efficient too. Because if I read this, I don't have to convert it from a string into an integer by calling a to I, a to f, or whatever, right? It's already in the format that I'm expecting. And for that, instead of using for write, you would use for read. Otherwise, it's exactly the same thing that I would pass in here, right? Put into X, whatever you read from F, read that many bytes of that many things, right? And so the reason that it asks you how many things you want to write is because if you want to write an entire array, right, then you would say, I've got 5 integers in that array, and I want to write them all at once. Right? You'll go through an exercise that will show you the difference between these two. You don't have to write any code in your lab tomorrow, but you'll see how big of a file savings there is when you use binary data instead. Okay? All right, any questions? No? All right, keep it simple. Use forgets, use fgetc, use fprintf, cut, paste all the knowledge that you have about printf, and you're good to go. All right, see you on Wednesday.